There is a secret hidden in every beam of light, every falling stone, every orbiting planet, and every quantum transition in every atom in the universe. The secret is this: nature does not merely do things. Nature does things in the best possible way. Every physical process, without exception, follows the most efficient path available to it. Light travels between 2 points along the path that takes the least time. A ball thrown through the air follows the trajectory that minimizes a specific mathematical quantity called the action. A planet orbits its star along the path that optimizes the balance between kinetic and potential energy. And a quantum particle, transitioning from one state to another, explores every possible path simultaneously and selects through a mechanism that Feynman described as the deepest principle in all of physics, the path that minimizes the action. This is the principle of least action. It is the most fundamental, the most universal, and the most beautiful principle in physics. It underlies Newton's laws of motion, Maxwell's equations of electromagnetism, Einstein's equations of general relativity, and the standard model of particle physics. Every known physical law can be derived from it. Every known physical phenomenon obeys it, and no exception to it has ever been found in any domain of physics, at any scale, in any context, in the entire history of science. The principle raises a question that has troubled and inspired physicists, mathematicians, and philosophers for over 3 centuries. Why? Why is nature efficient? Why does every physical process follow the optimal path? Why does the universe behave as if it were choosing the best option from among all available alternatives? Is the efficiency a mathematical accident, a consequence of the equations that happens to produce optimal behavior without any deeper significance? Or is it a clue, a fingerprint of a deeper principle, a deeper order, a deeper intelligence that is hardwired into the mathematical structure of physical reality? The story begins with light. In 1662, the French mathematician Pierre de Fermat proposed a principle that would become one of the foundations of physics. Light, traveling between 2 points, always takes the path that minimizes the total travel time. This is Fermat's principle of least time. It is not merely an approximation or a useful rule of thumb. It is an exact, exceptionless law that governs every behavior of light in every optical system. Fermat's principle explains refraction, the bending of light as it passes from one medium to another. When light travels from air into water, it slows down, because water is denser than air and light travels more slowly through it. Snell's law, discovered empirically in the 17th century, describes the precise angle at which the light bends. But Fermat showed that Snell's law is not a fundamental law. It is a consequence of a deeper principle. The light bends at precisely the angle that minimizes the total travel time from the source to the destination. The light knows that it will travel more slowly in the water, and it adjusts its path through the air to compensate, entering the water at the angle that produces the fastest overall journey. Fermat's principle also explains reflection. When light bounces off a mirror, it follows the path of equal angles. The angle of incidence equals the angle of reflection. This is not a separate law. It is a consequence of Fermat's principle. The path of equal angles is the path that minimizes the total travel time from the source to the mirror to the destination. The light does not need to know about the law of reflection. It needs only to minimize its travel time, and the law of reflection follows automatically. The principle explains the focusing properties of lenses. A convex lens bends light so that parallel rays converge to a single point, the focus. The lens works because it is shaped so that all paths from a distant source to the focus take exactly the same travel time. The light that passes through the thick center of the lens is slowed more than the light that passes through the thin edges, and the difference in speed exactly compensates for the difference in path length, so that all paths arrive at the focus simultaneously. The lens does not merely bend the light, It equalizes the travel times, creating a point in space where all paths are optimal, where the principle of least time is satisfied by all rays simultaneously, and where the light naturally converges. The principle even explains mirages. When light travels through air of varying temperature, the hot air near a road surface, for example, it curves, because the speed of light varies with the air density, and the path that minimizes the total travel time is not a straight line, but a curve that takes advantage of the faster speed in the hot, less dense air near the surface. The mirage is not an illusion in the optical sense. It is the real path of real light, following Fermat's principle through a medium whose properties vary with height. The light is doing exactly what the principle requires, minimizing its travel time through an inhomogeneous medium. The word knows is in quotation marks, because it raises the question that Fermat's principle immediately provokes. How does the light know? How does a photon, at the moment it leaves the source, know the shape of the entire path it will follow, including the parts of the path it has not yet traversed? How does it know that there is water ahead, that the water is denser, that the optimal angle of entry is different from the straight line path? The light does not have a brain. It does not have sensors. It does not have a planning department that calculates the optimal route and issues instructions. And yet it behaves as if it does, as if it has surveyed the entire path in advance and chosen the option that minimizes the travel time. Fermat himself was troubled by this implication. His principle seemed to attribute purpose to light, to suggest that light was choosing its path in order to minimize travel time, the way a rational agent would choose the fastest route on a map. This was teleological reasoning in terms of goals and purposes rather than causes and mechanisms. And teleological reasoning had been banished from physics by the mechanical philosophy of Descartes and his contemporaries. Physics was supposed to explain phenomena through causes, not through purposes. Light was supposed to follow its path because of the forces acting on it, not because of the goal it was pursuing. The philosopher Pierre-Simon Laplace, a generation after Fermat, attempted to resolve the tension by arguing that the principle of least time is merely a mathematical reformulation of Huygens's wave theory of light, that the light does not choose its path but that the wavefronts propagate according to local rules, and the global optimization emerges as a consequence of the local propagation. The teleology is apparent, not real. The purpose is a mathematical artifact, not a physical cause. But Laplace's resolution raises a further question. Why do the local rules produce global optimization? Why does the local propagation of wavefronts result in the global minimization of travel time? The local rules could, in principle, produce any behavior random, chaotic, inefficient, wasteful, but they do not. They produce optimal behavior, and the question of why the local rules are structured so as to produce global optimization is the same question that the teleological interpretation raises, merely displaced from the light to the laws that govern the light. The tension between the causal and the teleological interpretation of Fermat's principle has never been fully resolved, and it extends far beyond light. In 1744, the French mathematician Pierre-Louis Maupertuis generalized Fermat's principle from light to all of mechanics. Maupertuis proposed that every mechanical system, every moving object, every interacting particle, every physical process of any kind follows the path that minimizes a quantity he called the action. The action is defined as the integral of the kinetic energy minus the potential energy over the duration of the process. And Maupertuis's principle of least action states that the actual path taken by any physical system out of all the paths it could possibly take is the one for which the action is minimized. Maupertuis was explicit about the theological implications of his principle. He believed that the principle of least action was evidence of divine design, proof that God had created the universe according to the most efficient plan possible. The laws of movement and of rest, deduced from this principle being precisely the same as those observed in nature, Maupertuis wrote. We can admire the application of it to all phenomena, the movement of animals, the vegetative growth of plants, the revolutions of the stars, all are only its consequences, and the spectacle of the universe becomes so much the grander, so much more beautiful, the worthier of its author, when one knows that a small number of laws, most wisely established, suffice for all movements. Maupertuis's contemporaries were divided. The mathematician Leonhard Euler embraced the principle and developed its mathematical foundation with characteristic rigor, showing that the principle of least action could be formulated as a precise mathematical statement from which the equations of motion could be derived. The philosopher Voltaire ridiculed Maupertuis mercilessly, mocking both the principle and its theological pretensions in a series of savage satires, and the scientific community debated, for decades, whether the principle of least action was a genuine fundamental principle of physics, or merely a mathematical reformulation of Newton's laws that happened to take an optimization form. Euler, who was the greatest mathematician of the 18th century and a devout Christian, saw no conflict between the mathematical and the theological interpretation of the principle. He regarded the principle of least action as a mathematical expression of divine wisdom, as the language in which God's creative intelligence is written into the structure of the physical world. Euler wrote, "Since the fabric of the universe is most perfect and the work of a most wise creator, nothing at all takes place in the universe in which some rule of maximum or minimum does not appear." For Euler, the optimization was not a mathematical accident. It was the signature of the Creator, the mark of divine intelligence on the fabric of physical reality. The German mathematician Carl Friedrich Gauss, who followed Euler by a generation, expressed a similar view. God does arithmetic. The laws of physics are mathematical, not because mathematics is a human invention that happens to describe physical phenomena, but because the physical world is structured by a mathematical intelligence that operates according to optimization principles. The principle of least action is the most direct evidence for this view. The universe does not merely obey mathematical laws. It obeys the optimal mathematical laws, the laws that produce the most efficient, the most elegant, and the most economical behavior possible. The debate was settled decisively, permanently, and in favor of least action by the work of two mathematicians who transformed the principle from a curiosity into the foundation of all of physics. Joseph Louis Lagrange, working in the late 18th century, reformulated the entire Newtonian mechanics in terms of the principle of least action. Lagrange showed that Newton's three laws of motion, the law of inertia, the law of force and acceleration, and the law of action and reaction, are all consequences of a single, more fundamental principle, the principle that the action is minimized along the actual path of the system. Lagrange's reformulation was not merely a mathematical trick, it was a conceptual revolution. In Newton's framework, you specify the forces acting on the system and compute the motion that the forces produce. In Lagrange's framework, you specify the action, the mathematical quantity that nature minimizes, and derive the equations of motion from the requirement that the action is stationary. The forces do not appear in the fundamental formulation. They emerge as consequences of the optimization principle. The conceptual shift from Newton to Lagrange cannot be overstated. In Newton's framework, the fundamental entities are forces, pushes, and pulls that act on objects and determine their motion. The universe is a collection of objects interacting through forces. In Lagrange's framework, the fundamental entity is the action, a single mathematical quantity that encodes the entire dynamics of the system. The universe is not a collection of objects interacting through forces. It is a mathematical optimization problem whose solution is the behavior of everything in the universe. This shift changes the answer to the most basic question in physics. Why does the world behave the way it does? In Newton's framework, the answer is because forces push and pull objects along their trajectories. In Lagrange's framework, the answer is because the action is minimized. The forces are not the explanation. They are the consequence of the deeper principle that the action must be optimal. The forces are how the universe achieves the optimization. The optimization is the reason the forces have the values they have. This is a profoundly different picture of reality. Newton's universe is a machine, a collection of parts interacting through mechanical forces. Lagrange's universe is a mathematical poem, a single, elegant, all-encompassing principle that generates the entire behavior of the physical world through the requirement that a single quantity be optimal. The machine picture says, the world is what it is because of the forces. The optimization picture says, the world is what it is because it is the best it can be. The philosopher Gottfried Wilhelm Leibniz anticipated this picture with his famous claim that our universe is the best of all possible worlds. Leibniz argued that God, being infinitely wise and infinitely good, he would create the world that maximized goodness while minimizing complexity, the world that achieved the greatest richness of phenomena with the simplest set of laws. Voltaire ridiculed Leibniz's optimism in Candide, but the principle of least action vindicated Leibniz's mathematical intuition. The universe does, in fact, operate according to an optimization principle that produces the most efficient behavior from the simplest possible framework. The world may or may not be the best of all possible worlds in the moral sense, but it is, provably, the most efficient of all possible worlds in the mathematical sense. William Rowan Hamilton, working in the 1830s, extended Lagrange's reformulation into a framework of extraordinary power and elegance. Hamilton showed that the principle of least action applies not only to classical mechanics but to optics, to wave phenomena, and potentially to any physical system that can be described by a mathematical action. Hamilton's formulation, Hamiltonian mechanics, became the language in which quantum mechanics was later formulated, and it remains the standard framework for all of theoretical physics. Hamilton's framework revealed something that neither Newton nor Lagrange had fully appreciated: the deep connection between the principle of least action and the structure of time. In Hamiltonian mechanics, the action is the integral over time of the difference between kinetic and potential energy. The equations of motion that minimize the action are Hamilton's equations, a set of coupled differential equations that describe the evolution of the system in terms of generalized coordinates and generalized momenta. And these equations have a mathematical structure, a symplectic structure, that preserves certain quantities over time, including the total energy, the total momentum, and the total angular momentum. The conservation laws are not additional assumptions. They are consequences of the action principle, consequences that Noether would later make precise in one of the most beautiful theorems in all of mathematics. The universality of the principle of least action is staggering. Every known physical law can be derived from an action principle. Newton's mechanics, derived from the action. Maxwell's electromagnetism, derived from the action. Einstein's general relativity, derived from the Einstein-Hilbert action. The standard model of particle physics, derived from the standard model action. Quantum electrodynamics, quantum chromodynamics, the electroweak theory, string theory, loop, quantum gravity. Every physical theory that has ever been formulated can be expressed as the requirement that a specific action is minimized along the actual path of the system. There is no exception. There is no known physical phenomenon that does not obey an action principle. And there is no known physical theory that cannot be reformulated in terms of the minimization of an action. The principle of least action is not one law among many. It is the law from which all other laws follow. It is the master equation of the universe, the single, overarching principle that generates every known physical law as a special case. The physicist Richard Feynman, who developed the path integral formulation of quantum mechanics, and who had as deep an intuition for the structure of physics as any human being who has ever lived, described the principle of least action as the most fundamental principle in all of physics. Feynman's lectures on the topic, delivered at Caltech in the 1960s, are among the most celebrated lectures in the history of science. In them, Feynman described the principle with the awe of a scientist who has spent his life studying the deepest structure of reality and who finds at the bottom a principle of breathtaking simplicity and breathtaking mystery. Feynman's awe was directed at a specific feature of the principle, its apparent teleology. The principle of least action describes the behavior of physical systems in terms of a global optimization, the minimization of a quantity over the entire path from beginning to end. The system does not merely respond to local forces at each moment, the way Newton's laws describe. It behaves as if it knows the entire path in advance and has chosen the optimal one. The ball thrown through the air does not merely respond to gravity at each instant. It follows the trajectory that minimizes the total action over the entire flight, from launch to landing. The light beam does not merely respond to the change in density at the air-water interface. It follows the path that minimizes the total travel time from source to destination, including the parts of the path it has not yet traversed. How does the system know? How does the ball know where it will land? How does the light know what medium it will enter? How does the planet know the shape of its orbit? The Newtonian answer is, it does not know. The optimization is a mathematical consequence of the local forces, not a cause of the motion. The ball follows the parabola because gravity pulls it downward at each instant, and the cumulative effect of the downward pulls happens to produce the action-minimizing path. The ball does not choose the path. The forces produce the path, and the path happens to minimize the action. But this raises the question, why do the local forces produce global optimization? Why does the cumulative effect of gravity at each instant produce a trajectory that minimizes the total action over the entire flight? The forces could, in principle, produce any trajectory, but they produce the optimal one. And the question of why the forces are structured so as to produce optimal trajectories is the question that the principle of least action raises, and that the Newtonian framework, by itself, cannot answer. This answer is mathematically correct, but it is deeply unsatisfying, for a reason that Feynman articulated with characteristic directness. We have a mathematical formulation that works perfectly. We can calculate anything with it, but we do not understand it. The least action principle is not the kind of principle that you can explain in simple terms. It is the kind of principle that makes you wonder whether nature is telling you something that you are not yet smart enough to understand. Feynman was not alone in his wonder. The Nobel laureate Paul Dirac, who first recognized the connection between the action principle and quantum mechanics, wrote, "It seems as if a purpose is built into the very structure of the physical world, as if the laws of physics are not merely descriptions of what happens, but prescriptions for what should happen." The word "should" is remarkable coming from a physicist of Dirac's stature. Dirac was one of the most rigorous and least sentimental physicists of the 20th century. His use of "should" indicates that the optimization character of physical law struck him as requiring an explanation that the physics alone does not provide. The mathematician Hermann Weyl, one of the deepest thinkers of the 20th century, expressed the same wonder in more philosophical terms. The world does not merely exist. It is structured as if it were designed. Designed not by an external agent, but by an internal principle of optimization that governs every process at every scale. Weyl's "as if" is important. He is not claiming that the world was designed by a designer. He is noting that the mathematical structure of physical law has the same character as the output of an optimization process, the same character as a system that has been fine-tuned to produce the best possible behavior from the simplest possible principles. The physicist Eugene Wigner, in his famous essay, The Unreasonable Effectiveness of Mathematics in the Natural Sciences, argued that the mathematical elegance of physical law, including the optimization character of the principle of least action, is a mystery that the natural sciences have not explained, and perhaps cannot explain. The miracle of the appropriateness of the language of mathematics for the formulation of the laws of physics, Wigner wrote, is a wonderful gift which we neither understand nor deserve. The principle of least action is the most concentrated expression of this miracle. The fact that the most fundamental law of physics takes the form of a mathematical optimization is, in Wigner's terms, a gift whose source and whose meaning remain unknown. The wonder that Feynman described has a specific, articulable content. The principle of least action suggests that the universe has a mathematical structure that is oriented toward optimization, that the laws of physics are not arbitrary rules imposed on an indifferent substrate, but expressions of a deeper principle that selects, from among all possible behaviors, the most efficient, the most elegant, and the most economical. The universe does not merely behave, it optimizes, and the optimization is not local, not sequential, not step by step. It is global, extending over the entire path, the entire system, the entire history of the process, as if the universe has access to the complete information about the process from beginning to end, and is selecting the path that optimizes the whole. The contemplative traditions have been describing this feature of reality for millennia. In Christianity, the concept of the logos, the rational, ordering, creative principle through which all things were made, describes a universe that is structured by divine reason. The logos is not a force that pushes matter around. It is the rational order that determines the structure of reality, the mathematical form, the logical coherence, the optimization principle that gives the universe its specific, elegant, efficient character. When the physicist discovers the principle of least action, they are discovering, in the Christian framework, the logos at work, the divine reason that has structured the universe according to the most efficient, the most beautiful, and the most mathematically elegant plan. The theologian Thomas Aquinas identified divine wisdom as the principle that governs the order of creation. In the Summa Theologica, Aquinas wrote, "God acts through wisdom, and wisdom is the principle of all order. The order of creation is not arbitrary. It is wise, governed by the divine wisdom that selects, from among all possible arrangements, the one that best expresses the divine nature. The principle of least action is, in Aquinas' framework, an expression of divine wisdom, the physical law that instantiates the divine preference for efficiency, elegance, and economy in the structure of the created world." In Buddhism, the concept of dharma has a dual meaning that is directly relevant. Dharma means both teaching and law, both the Buddha's instruction and the natural order that the instruction describes. The universe operates according to dharma, according to a lawful, ordered, non-arbitrary pattern that is neither random nor imposed from outside, but inherent in the structure of reality itself. The principle of least action is an expression of dharma, the natural law that governs the behavior of all physical systems, that operates without an external enforcer, and that produces, through its own inherent logic, the optimal behavior that every physical process displays. The Buddhist concept of dependent origination, pratitya samutpada, describes a universe in which every phenomenon arises from the optimal conjunction of conditions. Nothing arises randomly, nothing arises without cause, and the specific conditions from which each phenomenon arises are not arbitrary, They are the conditions that produce this specific phenomenon with this specific character at this specific moment. The principle of least action is the mathematical expression of this non-arbitrariness. Every physical process follows the path that the specific conditions determine to be optimal, producing the specific behavior that the conjunction of conditions requires. In Islam, the concept of hikmah, divine wisdom, describes the quality of God's creative activity that produces the most excellent, the most balanced, and the most purposeful arrangement of all things. The Quran states, "You do not see any inconsistency in the creation of the most merciful. So look again. Do you see any flaw?" The flawlessness of creation is not merely aesthetic. It is structural, the absence of waste, the absence of redundancy, the absence of inefficiency in the mathematical laws that govern the physical world. The principle of least action is the physicist's discovery of this hikmah, the divine wisdom that has structured the physical laws according to the most efficient, the most flawless, the most wasteless principle available. In Judaism, the concept of hikmah, wisdom, is personified in the book of Proverbs as a divine attribute that was present at the creation and that served as the master craftsman through which God structured the world. The Lord by wisdom founded the earth. By understanding he established the heavens. Proverbs 3:19. Hikmah is not merely a quality of God's mind. It is the principle by which the world was made, the structural intelligence that determined the form, the order, and the mathematical properties of the created universe. The principle of least action is, in the Jewish framework, the physicist's discovery of hikmah at work, the mathematical expression of the divine wisdom that structured the universe according to the most efficient and the most elegant principle available. The Kabbalistic tradition's concept of the Sephirot, the 10 divine emanations through which God creates and sustains the world, includes the Sephirah of Hikmah as the first emanation after the Keter, the crown, the infinite divine will. Hikmah is the first differentiation of the divine will into specific form, the first moment at which the infinite potentiality of the divine becomes structured, ordered, and mathematically precise. The principle of least action, in the Kabbalistic framework, is the mathematical expression of this first structuring, the optimization principle that transforms the infinite potentiality of the divine will into the specific, ordered, efficient structure of the physical world. In Hinduism, the concept of rita, the cosmic order, the lawful pattern that governs the unfolding of the universe, is the Vedic expression of the same insight. The Rig Veda describes rita as the principle that sustains the movement of the sun, the cycle of the seasons, the behavior of fire, and the order of the cosmos. Rita is not imposed from outside by an arbitrary authority. It is the inherent order of reality, the natural, lawful, mathematically precise pattern that the universe follows, because it is the nature of the universe to follow it. The principle of least action is the modern physicist's formalization of rita, the precise, mathematical expression of the cosmic order that the Vedic seers perceived through their contemplative insight 3,000 years before. Lagrange and Hamilton gave it its mathematical form. In the next stage, we will examine how Richard Feynman's path integral formulation of quantum mechanics transforms the principle of least action from a mysterious optimization principle into a specific, calculable, quantum mechanical process, and how Noether's theorem connects the principle to the deepest symmetries of physical law. Because the mystery of least action, the mystery of how the universe optimizes, has a specific quantum mechanical answer. And the answer reveals something about the mathematical structure of reality that every contemplative tradition has been describing in its own language. The universe is not merely efficient, it is perfectly efficient, and the perfection is not accidental. It is the deepest feature of the mathematical structure that governs all physical phenomena, a feature that the physics describes with precision, but that only the convergence of physics and the contemplative traditions can begin to explain. The principle of least action is not merely a law of physics. It is a statement about the character of the universe. And the character it describes is one that every contemplative tradition in every language has identified as the signature of the divine: wisdom, efficiency, elegance, and the relentless preference for the best possible path through the landscape of possibility. We have established that the principle of least action is the most fundamental law in physics, the single principle from which every known physical law can be derived. The optimization requirement that every physical process obeys without exception. Light follows the path of least time. Particles follow the trajectory of least action. Planets follow the orbit that minimizes the action integral. And the question that the principle raises, how does the system know which path is optimal, has troubled physicists from Fermat to Feynman. Now we must examine the two discoveries that transform the principle of least action from a mysterious optimization principle into the deepest window we have into the mathematical structure of reality. The first is Richard Feynman's path integral formulation of quantum mechanics, which reveals how nature actually implements the optimization. The second is Noether's theorem, which reveals that every optimization principle is connected to a conservation law, and that the symmetries of the action determine the conserved quantities of the universe. Together, these two discoveries constitute the most profound insight into the nature of physical law that the 20th century produced. And they raise the question of why the mathematical structure of reality is so beautiful, so symmetric, and so perfectly organized that the deepest truths of physics can be expressed as requirements of mathematical elegance. Let us begin with Feynman. In 1948, Richard Feynman, then a young physicist at Cornell University, published a paper that reformulated quantum mechanics from the ground up. The paper, Space-Time Approach to Non-Relativistic Quantum Mechanics, introduced the path integral formulation, a framework that would become one of the most powerful and most widely used tools in all of theoretical physics. Feynman's insight began with a question. In classical mechanics, a particle follows a single path, the path that minimizes the action. But quantum mechanics says that particles do not have definite paths. A quantum particle does not travel along a single trajectory from A to B. It exists in a superposition of all possible trajectories simultaneously. So how does the principle of least action work in the quantum world? If the particle does not follow a single path, what does it mean to say that the path minimizes the action? Feynman's answer was revolutionary. The quantum particle follows all paths, every path, without exception. From the source to the destination, the particle takes every conceivable route: straight lines, curved lines, zigzag lines, loops, spirals, paths that go to the edge of the universe and back, paths that travel backward in time and then forward again, paths that violate every intuition about what a reasonable trajectory should look like. The particle takes all of them, simultaneously, in quantum superposition. This is one of the most radical claims in the history of physics. It is not a metaphor. It is not an approximation. It is the literal, mathematically precise content of Feynman's path integral. The probability, amplitude, for a particle to go from point A to point B is the sum of the amplitudes for every possible path from A to B. Every path means every path, including paths that travel faster than light, paths that zigzag through the interior of the sun, paths that circle the galaxy before arriving at B, and paths that visit every point in the universe before reaching their destination. The sum is infinite, the paths are uncountable, and every one of them contributes to the final amplitude. The physicist Freeman Dyson, who was one of the first to recognize the power of Feynman's approach, described it as the replacement of the Newton picture, in which the particle follows a single, predetermined path with the democracy of paths, in which every possible path has an equal right to contribute to the outcome. And the classical path emerges not by fiat, but by democratic vote. The classical path wins the vote because it has the most support, the most constructive interference from nearby paths. But every other path votes too, and the tiny contributions of the non-classical paths produce the quantum corrections that distinguish quantum mechanics from classical mechanics. The path integral is not merely a computational tool. It is a statement about the ontology of the quantum world. The quantum particle does not follow a path. It is a superposition of all paths. The classical path is not the reality. It is the dominant approximation to a reality that includes every possible trajectory, weighted by its phase, interfering with every other trajectory, producing, through the mathematics of complex exponentials, the specific, definite, observable behavior that we call the physical world. But the paths do not contribute equally. Each path carries a weight, a probability amplitude that is determined by the action along that path. The amplitude is proportional to a complex number whose phase is the action divided by Planck's constant. Paths with very different actions have very different phases, and when these phases are added together, they cancel each other out the way. Waves with different wavelengths cancel when they interfere destructively. Paths with similar actions have similar phases, and these phases add constructively, reinforcing each other, amplifying each other, producing a strong combined amplitude. The classical path, the path that minimizes the action, is the path around which all nearby paths have similar actions and therefore similar phases. The nearby paths interfere constructively, producing a large combined amplitude. Paths far from the classical path have very different actions and very different phases, and they cancel each other out through destructive interference. The result is that the particle's probability is concentrated around the classical path, the path of least action, with quantum corrections that become negligible for macroscopic objects. This is the answer to the mystery of how the system knows which path is optimal. The system does not know. It does not need to know. The system takes all paths simultaneously, and the mathematical structure of quantum mechanics, the interference of probability amplitudes, automatically selects the optimal path through the cancellation of suboptimal paths. The optimization is not a choice. It is an interference effect. The universe does not choose the best path. It tries all paths, and the best path is the one that survives the interference. The implications of Feynman's path integral are staggering. First, it resolves the teleological puzzle. The particle does not need to know the future in order to follow the optimal path. It does not need to survey the entire trajectory in advance and select the best option. It simply takes all paths simultaneously, and the quantum interference does the selecting. The apparent teleology, the appearance that the particle is choosing its path in order to minimize the action, is produced by the interference of amplitudes, not by any planning or foresight on the part of the particle. The optimization is emergent from the quantum mechanics, not imposed from outside. This resolution of the teleological puzzle is one of the deepest insights in the history of science. For 3 centuries, the apparent teleology of the principle of least action had puzzled physicists and philosophers. How can a physical system behave as if it has a goal? How can it appear to choose the optimal path without having the capacity to choose? Feynman's answer dissolves the puzzle. The system does not choose. It explores every option simultaneously, and the mathematics of quantum interference selects the optimal path from among all the options. The teleology is real, the optimal path is really followed. But it is not the product of foresight or planning. It is the product of the most democratic process imaginable. Every possible path contributes, and the optimal path wins, because it has the most quantum support. The philosopher of science Michael Friedman has described Feynman's resolution as the naturalization of teleology, the the demonstration that goal-directed behavior can arise from a process that has no goals, no intentions, and no awareness. The universe does not need to be intelligent to be efficient. It needs only to be quantum, and the quantum mechanics automatically produces the efficiency through the interference of amplitudes, the same mechanism that produces the diffraction patterns of light, the tunneling of particles through barriers, and every other quantum phenomenon that has ever been observed. Second, it reveals that the classical world is a special case of the quantum world. The classical path, the single, definite, action-minimizing trajectory that Newton's mechanics describes, is not the fundamental reality. It is the dominant contribution to a sum over all possible paths that quantum mechanics performs. The classical world emerges from the quantum world through the mathematical mechanism of constructive interference around the action-minimizing path. The classical world is not separate from the quantum world. It is the quantum world seen at a scale where the interference pattern is so sharp that only the optimal path is visible. Third, it reveals the universe as a vast, continuous, all-encompassing computation. The path integral is a sum and integral over all possible configurations of the system, weighted by the exponential of the action. The universe is, in Feynman's framework, computing the path integral at every moment, for every system, over all possible paths simultaneously. The computation is quantum performed in superposition, with the amplitudes interfering to select the optimal outcome, and the output of the computation is the classical world of definite trajectories, definite positions, and definite physical events that we observe. The connection to our investigation of evolution is direct. In our investigation of evolution as a quantum algorithm, we propose that evolution exploits the computational properties of quantum mechanics, quantum tunneling, to cross fitness valleys, quantum annealing to find global optima, and quantum superposition to explore multiple solutions simultaneously. Feynman's path integral reveals the general framework in which this quantum computation operates. The universe explores all possibilities simultaneously and selects the optimal outcome through interference. Evolution is a specific application of this general principle, the biological implementation of the universal quantum optimization that the principle of least action describes. Feynman's path integral also provides the framework for understanding the relationship between the quantum Zeno effect and the principle of least action. In the Zeno effect, continuous observation freezes a quantum system by projecting it at every moment into a definite state. In the path integral framework, the continuous observation constrains the sum over paths, restricting the paths that the system can explore, eliminating the paths that the observation rules out, and forcing the sum to converge on a narrow set of paths that are compatible with the observed state. The Zeno effect is the observation's restriction of the path integral, and the principle of least action is the path integral's selection of the optimal path from among those that the observation permits. The two principles are complementary. The Zeno effect determines which paths are available, and the least action principle determines which available path is selected. The path integral, the Zeno effect, and the principle of least action form a trinity of principles that, taken together, describe the deepest mechanism of physical reality. The path integral says, the universe explores all possibilities. The least action principle says, the optimal possibility is selected. The Zeno effect says, the selected possibility is sustained by observation. Together, they describe a universe that is simultaneously creative, exploring all paths, intelligent, selecting the best path, and sustained, maintaining the selected path through continuous observation. The creation, the selection, and the sustaining are not separate processes. They are three aspects of a single, continuous, quantum mechanical process that constitutes the moment-by-moment unfolding of physical reality. Now let us turn to the second great discovery, Noether's theorem. In 1918, the German mathematician Noether proved a theorem that is widely regarded as one of the most beautiful and most important results in the history of mathematics and physics. Noether's theorem states, for every continuous symmetry of the action, there is a corresponding conserved quantity. The theorem provides a precise, mathematical, one-to-one correspondence between symmetries and conservation laws, a correspondence that reveals the deepest structure of physical law. The theorem is remarkable for multiple reasons. First, it is completely general. It applies to any physical system described by an action which, as we have established, is every physical system that has ever been studied. Second, it is constructive. It does not merely assert that conservation laws exist. It provides a specific, algorithmic procedure for deriving the conserved quantity from the symmetry. Given the symmetry, Noether's theorem tells you exactly what is conserved and how to calculate it. Third, it is exact. The conservation law is not approximate. It holds with perfect precision at every moment, for every system, without exception. And fourth, it is beautiful. The correspondence between symmetries and conservation laws is one-to-one, clean, and mathematically elegant, a perfect mapping between two fundamental features of physical reality that had previously been considered unrelated. Noether herself was denied a faculty position at the University of Göttingen because she was a woman, despite having proved what Einstein called the most important mathematical theorem ever proved in the development of modern physics. She taught without pay for years. Was expelled from Germany by the Nazis in 1933 because she was Jewish, and died in the United States in 1935 at the age of 53. Her theorem outlived the prejudices that constrained her career and has become the foundation of every branch of modern theoretical physics. The theorem works as follows. A symmetry of the action is a transformation that leaves the action unchanged. If you perform the transformation and the action has the same value afterward as it did before, the action has a symmetry under that transformation. And Noether's theorem guarantees that this symmetry produces a conserved quantity, a physical quantity that does not change over time, that is preserved throughout the evolution of the system, and that provides an absolute, permanent, inviolable constraint on the system's behavior. The examples are among the most fundamental results in physics. Time symmetry. The action of a closed system does not change if you shift the time coordinate. If you perform the experiment today or tomorrow, the physics is the same. This time symmetry produces, through Noether's theorem, the conservation of energy. Energy is conserved because the laws of physics do not change over time. The conservation of energy is not an independent law. It is a consequence of the time symmetry of the action. Spatial symmetry. The action does not change if you shift the spatial coordinates. If you perform the experiment here or there, the physics is the same. This spatial symmetry produces the conservation of momentum. Momentum is conserved because the laws of physics do not change from one place to another. Rotational symmetry. The action does not change if you rotate the spatial coordinates. If you perform the experiment facing north or facing east, the physics is the same. This rotational symmetry produces the conservation of angular momentum. Gauge symmetry. The action of electromagnetism does not change if you multiply the wave function of every charged particle by a position-dependent phase factor, a transformation that has no physical significance for any individual particle, but that changes the mathematical description of the electromagnetic field. This gauge symmetry produces the conservation of electric charge, the most precisely tested conservation law in physics, confirmed to better than 1 part in 10 to the 21st. The pattern extends to every known conservation law. The conservation of baryon number arises from a symmetry of the strong force action. The conservation of lepton number arises from a symmetry of the weak force action. The conservation of CPT, the combined symmetry of charge conjugation, parity, and time reversal, is a consequence of the Lorentz symmetry of the action in relativistic quantum field theory. Every conservation law is a symmetry. Every symmetry is a property of the action, and the action is the quantity that the principle of least action optimizes. The physicist David Gross, who shared the 2004 Nobel Prize for the discovery of asymptotic freedom, described Noether's theorem as the principle that symmetry dictates interaction. The forces of nature are not free parameters that God could have set to any values. They are determined by the symmetries of the action. Change the symmetries, and you change the forces. Change the forces, and you change the universe. The specific universe we inhabit with its specific forces, its specific conservation laws, and its specific physical behavior is determined by the specific symmetries of the specific action that the principle of least action optimizes. The universe is, at the deepest level, a consequence of a mathematical structure, a structure whose properties are determined by symmetry and whose behavior is determined by optimization. Each conservation law that physics has discovered is the consequence of a symmetry of the action, and each symmetry of the action is a statement about the mathematical structure of the physical law, a statement that the law has a specific invariance, a specific unchangingness, a specific permanence under a specific class of transformations. The conservation laws are not arbitrary rules imposed on the universe from outside. They are consequences of the symmetries of the action, consequences of the mathematical structure of the optimization principle that governs all physical processes. The depth of Noether's theorem cannot be overstated. It reveals that the most fundamental features of physical reality, the conservation of energy, the conservation of momentum, the conservation of charge, the conservation of every quantity that physics has identified as conserved, are all consequences of symmetries. And the symmetries are all properties of the action, properties of the single mathematical quantity that the principle of least action minimizes. The entire structure of physical law, every conservation law, every symmetry, every fundamental constant flows from the action. And the action is a single mathematical expression that encodes the complete dynamics of the physical system. The physicist Chen-Ning Yang, one of the greatest physicists of the 20th century, described Noether's theorem as the most important theorem in physics. The mathematician Yuri Manin called it one of the most beautiful results in mathematical physics, and the physicist Leon Lederman, in his popular book The God Particle, wrote, "Noether's theorem is to physics what natural selection is to biology, the unifying principle that makes sense of everything else. The gauge symmetries of the standard model of particle physics provide the most dramatic application of Noether's theorem. The standard model describes all known fundamental forces, electromagnetism, the weak nuclear force, and the strong nuclear force as consequences of gauge symmetries of the action. The electromagnetic force arises from a U1 gauge symmetry. The weak force arises from an SU2 gauge symmetry. The strong force arises from an SU3 gauge symmetry. And each force is associated with a conserved quantity, electric charge, weak isospin, and color charge, respectively. The forces of nature are not separate, independent entities that happen to coexist in the universe. They are consequences of the symmetries of the action, mathematical properties of the optimization principle that governs all physical processes. The strong force that confines quarks, the electromagnetic force that binds atoms, the weak force that drives radioactive decay, all of these emerge from the requirement that the action be invariant under specific mathematical transformations. The forces are not fundamental. The symmetries are fundamental, and the symmetries are properties of the action, properties of the principle of optimization, that every contemplative tradition has identified, in its own language, as the signature of divine order. The connection between symmetry and beauty is not accidental. The physicist Paul Dirac, who formulated the Dirac equation that describes the electron and that predicted the existence of antimatter, famously stated, "It is more important to have beauty in one's equations than to have them fit experiment." Dirac's criterion of beauty was not aesthetic whimsy. It was a methodological principle grounded in the repeated experience of theoretical physics. The most beautiful equations, the most symmetric, the most elegant, the most economical, have consistently turned out to be the correct ones. The history of physics is a history of beautiful equations being confirmed by experiment and ugly equations being discarded. The physicist Steven Weinberg, in his Nobel lecture, described the experience of discovering the electroweak theory, the theory that unifies electromagnetism and the weak nuclear force, as an experience of recognizing beauty. "Our mistake is not that we take our theories too seriously," Weinberg wrote, "but that we do not take them seriously enough." It is always hard to realize that these numbers and equations we play with at our desks have something to do with the real world. The beauty of the equations is not a human projection onto an indifferent mathematical structure. It is a genuine property of the structure, a property that physicists learn to perceive through decades of training, that they rely on as a guide in constructing new theories, and that has been confirmed again and again as a reliable indicator of truth. The mathematician Roger Penrose has distinguished between three kinds of beauty in physics: the beauty of a specific equation, like Dirac's equation for the electron, the beauty of a theoretical framework, like general relativity, and the beauty of a principle, like the principle of least action. The principle of least action is, in Penrose's classification, the most beautiful entity in physics because it is the most universal, the most economical, and the most productive of physical law. A single principle, applied to a single quantity, generates the entire structure of every known physical theory. There is nothing in physics that is more beautiful, more economical, or more productive than this. This raises a question that physics cannot answer, but that the contemplative traditions have been addressing for millennia. Why is the mathematical structure of physical reality beautiful? Why do the laws of physics exhibit the symmetries that Noether's theorem connects to conservation laws? Why is the action, the fundamental quantity that nature optimizes, structured in a way that produces elegant, symmetric, conservation law-generating mathematics? The physics can describe the beauty. It can formalize the beauty in precise mathematical terms, but it cannot explain why the beauty exists. The beauty of physical law is, in Wigner's famous phrase, an unreasonable fact, a fact that the physics describes, but that the physics alone cannot account for. The contemplative traditions offer an answer. In Christianity, the beauty of physical law is understood as a reflection of the beauty of the divine mind. Augustine wrote, "Numbers do not come from the things we count. They come from God." The mathematical structure of reality, the symmetries, the conservation laws, the optimization principles, is not an accidental feature of a godless universe. It is the expression of the divine logos, the rational, creative, mathematically precise mind of God, whose thoughts are the laws of physics and whose beauty is the beauty of the equations that describe them. The physicist who discovers a beautiful equation is not merely finding a pattern in the data. They are glimpsing the mind of God, perceiving, through the language of mathematics, the rational order that the Logos has inscribed in the structure of physical reality. The theologian Hans Urs von Balthasar developed this into a comprehensive theology of beauty. Von Balthasar argued that beauty is not a subjective preference but an objective attribute of being, that the beautiful reveals the true, and that the mathematical beauty of physical law is a genuine perception of the divine order that constitutes the deepest structure of reality. The principle of least action is, in von Balthasar's framework, the most concentrated expression of this divine beauty, the single, elegant, all-encompassing principle that generates the entire structure of physical law through the simple requirement of optimization. In Buddhism, the beauty of physical law is understood through the concept of the dharmata, the nature of dharma, the intrinsic order and structure of reality that is neither created by God nor imposed from outside, but that is the inherent, self-existing, mathematical structure of the way things are. The dharmata is beautiful, not because it was designed to be beautiful, but because beauty is the nature of reality when reality is perceived clearly. The principle of least action in the Buddhist framework is the physicist's perception of the dharmata, the mathematical structure of reality as it is, perceived through the instruments of physics rather than through the instruments of meditation, but perceived nonetheless. The Zen tradition captures the aesthetic dimension with characteristic directness. The master Rikyū, the founder of the Japanese tea ceremony, described the aesthetic of wabi-sabi, the beauty of simplicity, imperfection, and transience. The principle of least action embodies wabi, the beauty of maximum simplicity, of doing the most with the least, of achieving the entire structure of physical law from a single, simple, elegant principle. The universe is not Baroque. It is wabi, stripped to its essence, reduced to its most fundamental principle, expressing the maximum of physical law through the minimum of mathematical structure. In Islam, the beauty of physical law is understood through the divine name Al-Musawwir, the fashioner, the one who gives form to creation with artistic precision and aesthetic perfection. The Quran describes God as the one who has given everything its form, 2050, and who created everything in the best proportion, 25:2. The mathematical proportions of physical law, the symmetries, the conservation laws, the optimization principles, are the artist's signature on the canvas of creation. The physicist who discovers Noether's theorem is reading the signature, deciphering the mathematical calligraphy in which the divine fashioner has inscribed the order of the universe. The Islamic tradition of sacred geometry, the intricate, mathematically precise, infinitely repeating patterns that adorn every mosque, every Quran, every work of Islamic art, is the artistic expression of the same insight. The geometric patterns are not mere decoration. They are visual representations of the mathematical order that the divine fashioner has embedded in the structure of reality. The symmetries of the geometric patterns, their translational invariance, their rotational invariance, their scale invariance are visual analogues of the gauge symmetries that Noether's theorem connects to the fundamental forces of nature. The mosque is a visual proof of the principle of least action, the demonstration, in stone and tile and light, that the mathematical structure of reality is symmetric, beautiful, and ordered by a principle of optimization that the physicist and the artist perceive through different instruments, but that both recognize as the deepest truth about the way the world is made. In Judaism, the concept of Tiferet beauty, the sixth of the 10 Sephirot in Kabbalistic thought, holds a central position in the tree of life, mediating between the expansive love of Hesed and the contracting judgment of Gevurah. Tiferet is the principle of harmony, the balanced, symmetric, optimally proportioned arrangement of opposing forces that produces the beauty of the created order. The principle of least action is, in the Kabbalistic framework, the physical expression of Tiferet, the principle that balances kinetic and potential energy, that harmonizes the expansion of motion with the contraction of force, and that produces, from the opposition of these two tendencies, the perfectly proportioned, symmetrically balanced, optimally efficient behavior that every physical system displays. The Talmudic dictum that God looked into the Torah and created the world, Bereshit Rabbah 1-1, implies that the mathematical structure of creation pre-exists in the divine wisdom, that the laws of physics are not arbitrary rules imposed after the fact, but expressions of the rational order that the divine mind contemplated before the act of creation. The principle of least action in this framework is the Torah of physics, the pre-existing rational order that God contemplated and that the physical world instantiates. The physicist who discovers the principle is reading the same Torah that God read before creating the world perceiving, through the instruments of mathematics, the same rational order that the divine mind contemplated in the pre-creation eternity. In Hinduism, the concept of Sundaram, beauty, one of the three attributes of Brahman, alongside Sat, being, and Chit, consciousness, establishes beauty as a fundamental attribute of ultimate reality. Brahman is not merely real and not merely conscious. Brahman is beautiful, inherently, necessarily, constitutively beautiful. And the beauty of the physical world, the mathematical elegance of the laws of physics, the symmetric perfection of the fundamental constants, the optimization of every physical process by the principle of least action is the expression of Brahman Sundaram in the manifest world. The beauty is not added to reality from outside. It is the nature of reality, the way reality looks when it is perceived clearly, the way the divine appears when it manifests in mathematical form. In the next stage, we will deepen the exploration of the tradition's understanding of the divine order that the principle of least action reveals. Because the principle does not merely describe a universe that is efficient. It describes a universe that is perfectly ordered by a principle that is simultaneously the most fundamental law of physics and the most concentrated expression of the divine wisdom that every contemplative tradition has, identified as the ground of reality. And the question of whether this order is a meaningless mathematical accident or a fingerprint of something deeper is the question that this investigation will pursue to its conclusion. We have now established that the principle of least action is the most fundamental law in physics, that Feynman's path integral reveals the quantum mechanism by which nature implements the optimization, and that Noether's theorem connects the optimization to the deepest symmetries of physical law. The universe optimizes. The optimization is implemented by quantum interference, and the symmetries of the optimization produce the conservation laws that govern every physical process. Now we must go deeper into what the contemplative traditions say about the rational order that the principle of least action reveals. Because the traditions do not merely assert that the universe is ordered, they describe the nature of the order, the source of the order, and the relationship between the order of the universe and the nature of the divine, and their descriptions, developed over millennia through contemplative insight rather than mathematical analysis, converge on the same structure that the physics reveals. A universe whose deepest law is a principle of optimization, whose optimization produces beauty, and whose beauty is the signature of a rational intelligence that is hardwired into the mathematical fabric of reality. We will begin with Christianity, whose concept of the Logos provides the most developed philosophical framework for understanding the rational order of the universe. The concept of the Logos has a dual origin, Greek philosophy and Hebrew theology. In Greek philosophy, the Logos was introduced by the pre-Socratic philosopher Heraclitus, who used it to describe the rational principle that governs the flux of the natural world. For Heraclitus, the world is in constant change. Everything flows, but the change is not random. It is governed by the Logos, the rational pattern that determines the structure, the sequence, and the proportion of all change. The Logos is not a god, it is not a person. It is the rational order itself, the mathematical structure of the world, the principle of proportion and harmony that makes the flux intelligible rather than chaotic. The Stoic philosophers adopted Heraclitus's logos and developed it into a comprehensive cosmology. The Stoics argued that the logos is the organizing principle of the universe, the rational force that structures matter into ordered forms, that governs the motion of the stars, the growth of plants, and the behavior of animals, and that is present in the human mind as the capacity for rational thought. The universe is not a collection of random events. It is a rational system governed by the logos, whose every process is determined by the same rational principle that the human mind uses when it reasons logically. The human capacity for reason is not an accident. It is the universe's rational structure becoming aware of itself in the human mind. The Neoplatonic philosopher Plotinus, in the 3rd century, developed the logos concept further by identifying it with the nous, the divine mind, the second hypostasis of the Neoplatonic one. The nous contains the forms, the mathematical patterns, the rational structures, the archetypal proportions that determine the form of every physical object and every physical process. The physical world is an image of the nous, a projection of the mathematical forms into material substance, governed by the rational proportions that the nous contains. The laws of physics, in Plotinus's framework, are the mathematical forms of the nous, projected into the material world, the rational structures of the divine mind, made manifest in the behavior of matter. The principle of least action would have been, for Plotinus, the most direct manifestation of the nous in the physical world, a single, rational, mathematical principle that generates the entire behavior of physical reality through the requirement of optimization. The optimization is the nous thinking the divine mind, contemplating the mathematical forms and projecting them through the principle of maximal efficiency into the material substrate of the physical world. The Gospel of John begins, "In the beginning was the Logos, and the Logos was with God, and the Logos was God." This opening sentence fuses the Greek philosophical concept with the Hebrew theological concept of the divine word, the creative speech by which God brings the world into existence. The Logos is simultaneously the rational order of the universe, the Greek meaning, and the creative will of God, the Hebrew meaning. The universe is rationally ordered because the rational order is divine. The mathematical structure of physical law is beautiful because the beauty is the expression of the divine mind. And the principle of least action is the physicist's discovery of the logos at its most fundamental level, the rational, optimizing, beauty-producing principle that governs every physical process in the universe. The early church fathers developed this fusion into a comprehensive theology of the rational universe. Justin Martyr, in the 2nd century, argued that the Greek philosophers had perceived the logos through reason, and that the Christian revelation was the completion of what reason had begun. The philosopher who perceives the rational order of the universe is perceiving the logos, the same logos that became incarnate in Christ. Clement of Alexandria went further, arguing that Greek philosophy was a schoolmaster that prepared the Greek world for the gospel, just as the Torah prepared the Jewish world. The rational order that the philosopher discovers and the divine truth that the theologian proclaims are not two different things. They are the same logos, perceived through different instruments, through reason by the philosopher and through revelation by the theologian. The medieval tradition's engagement with the rational order of the universe reached its pinnacle in the work of Thomas Aquinas. Aquinas synthesized Aristotelian philosophy with Christian theology, producing a comprehensive account of the relationship between divine reason and natural law. Aquinas argued that the natural law, the rational order that governs the physical world, is a participation in the eternal law, the rational order of the divine mind. The laws of physics are not separate from the divine mind. They are the divine mind's rational structure, participated in by the physical world, producing the specific, ordered, mathematically precise behavior that the physicist observes. Aquinas' concept of participation is particularly relevant to the principle of least action. The physical world participates in the divine rational order by instantiating the optimization principle in every physical process. The participation is not a copy or an image. It is a real, ontological sharing in the divine rationality, a sharing that gives the physical world its mathematical character, its symmetries, its conservation laws, and its beauty. The physicist who discovers these features is not merely mapping the physical world, they are tracing the pattern of participation, perceiving, in the mathematical structure of the physical world, the rational order of the divine mind in which the world participates. The 17th century astronomer Johannes Kepler expressed this with characteristic passion. The chief aim of all investigations of the external world should be to discover the rational order which has been imposed on it by God, and which he revealed to us in the language of mathematics. Kepler discovered the three laws of planetary motion laws that, as Lagrange later showed, are all consequences of the principle of least action applied to gravitational orbits. Kepler's discovery was, in his own understanding, a discovery of the divine language, the mathematical vocabulary, in which God's rational order is expressed in the motion of the planets. This theological framework has a specific implication for the principle of least action. The principle is not merely a mathematical regularity, it is the logos at work. The optimization is not merely an accident of the equations, it is the expression of divine rationality in the mathematical structure of physical law, and the physicist who discovers the principle is doing theology, perceiving the divine logos through the instrument of mathematics, just as the philosopher perceives it through the instrument of reason, and the mystic perceives it through the instrument of contemplation. The theologian Wolfhart Pannenberg developed this into the most comprehensive modern theology of science. Pannenberg argued that the laws of physics are not independent of God. They are expressions of the divine logos, the rational structure of the divine mind, projected into the created order, governing the behavior of every physical system through the mathematical precision that the divine mind embodies. The contingency of the laws, the fact that the laws could have been different, that the constants could have had different values, that the symmetries could have had different forms, is evidence that the laws are chosen, not necessary. And the specific laws that obtain the specific symmetries, the specific conservation laws, the specific optimization principle, are the specific expression of the divine choice, the logos selecting, from among all possible mathematical structures, the one that produces the most beautiful, the most efficient, and the most consciousness-producing universe. The physicist and Anglican priest John Polkinghorne has developed the most nuanced contemporary engagement with the principle of least action from a Christian perspective. Polkinghorne argues that the mathematical beauty and rationality of physical law is not proof of God's existence, but evidence of what he calls the intelligibility of the universe, the fact that the universe is structured in a way that can be understood by rational minds. This intelligibility is not guaranteed by the physics. It is a meta-feature of the physics, a feature that the laws of physics possess, but that the laws of physics do not explain. And the best explanation for the intelligibility, Polkinghorne argues, is that the universe is the product of a rational mind whose thoughts are the laws of physics, and whose rationality is the source of the intelligibility that physicists exploit when they discover beautiful mathematical principles. The principle of least action is, in Polkinghorne's framework, the most concentrated expression of the universe's intelligibility, a single, beautiful, rational principle that makes the entire behavior of the physical world comprehensible to the human mind. The fact that such a principle exists, the fact that the universe's behavior can be compressed into a single optimization requirement, is evidence of a rational order that transcends the physics and that points toward the rational ground from which the physics emerges. In Buddhism, The concept of dharma provides a different but complementary framework for understanding the rational order of the universe. The word dharma has multiple meanings in Buddhism. The Buddha's teaching, the natural law, the way things are, and the individual elements of experience. The multiplicity of meanings is not an ambiguity. It reflects the Buddhist insight that the teaching, the law, the reality, and the experience are not separate things. The Buddha's teaching is a description of the natural law. The natural law is the way things are, and the way things are is what the individual elements of experience display. The Dharma is simultaneously the truth, the law, the reality, and the teaching of all three. The Abhidharma, the systematic philosophical analysis of the Buddhist teachings, identifies specific dharmas that govern the behavior of the physical and mental worlds. These dharmas are not substances. They are processes, momentary, lawful, regularly arising events that constitute the flow of experience. And the laws that govern the dharmas are not imposed from outside by a lawgiver. They are intrinsic to the dharmas themselves, inherent in the nature of the processes, built into the structure of reality at the most fundamental level. This framework has a specific relevance to the principle of least action. In the Buddhist understanding, the optimization that physical systems display is not the result of a divine command or a cosmic plan. It is the intrinsic nature of the dharmas, the way the fundamental processes of reality naturally operate when they are not obstructed. The optimization is not imposed, it is inherent. The universe follows the path of least action not because a lawgiver has commanded it, but because the path of least action is the natural expression of the Dharma's intrinsic nature. The Madhyamaka philosopher Nagarjuna provides the deepest analysis of why the laws of nature have the form they do. Nagarjuna argues that all phenomena are empty of inherent existence, that nothing exists independently, that everything arises in dependence on conditions, and that the specific character of each phenomenon is determined by the specific conditions from which it arises. The laws of nature are not exceptions to this principle. They too are empty of inherent existence. They too arise from conditions. And the specific form that the laws take, the specific optimization principle, the specific symmetries, the specific conservation laws, is determined by the conditions of the universe in which they operate. This seems to contradict the idea that the laws are evidence of a rational order. If the laws are contingent, if they could have been different, then they do not reveal a necessary, eternal, rational principle. They reveal a specific, contingent, conditioned arrangement that could have been otherwise. But Nagarjuna's analysis cuts deeper. The contingency of the laws is itself the deepest truth about the rational order. The laws are rationally ordered not because they are necessary, but because the conditions from which they arise are rationally ordered. The optimization principle is not a necessary truth imposed on an indifferent universe. It is the natural expression of the conditions from which the universe arises, conditions that are themselves the expression of the Dharma, the lawful, ordered, non-arbitrary nature of reality. The Huayan Buddhist school's concept of the Dharma Dhatu, the realm of reality, the totality of all dharmas in their mutual interpenetration, provides the most comprehensive Buddhist framework for understanding the principle of least action. In the Dharma Dhatu, every dharma contains every other dharma. Every point of the universe reflects the entire universe, and the lawful order of the whole is present in every part. The principle of least action is not a law imposed on individual systems from outside. It is the expression of the Dharma Dhatu's inherent order in each individual process, the way each part of the universe reflects, in its own behavior, the optimal order of the whole. The Flower Ornament Sutra, the Avatamsaka, the foundational text of the Huayan school, describes the Dharma Dhatu with an image that directly parallels the principle of least action. In each dust mote of these worlds are inconceivable Buddha fields, in which all are perfectly revealed. The perfection that is perfectly revealed in each dust mote is not a transcendent perfection imposed from outside. It is the intrinsic perfection of the dharma, the optimal order that every phenomenon naturally displays when it is perceived clearly. The physicist who discovers the principle of least action is perceiving the perfection of the dust mote, the optimal order that every physical process naturally displays when it is analyzed mathematically. The Zen tradition's approach to the rational order of the universe is characteristically paradoxical. The Zen master does not seek to understand the rational order intellectually. They seek to perceive it directly, to see the order in the falling leaf, the flowing stream, the breaking wave, without the mediation of concepts, theories, or mathematical formulas. The Zen aesthetic of naturalness, the beauty of the unforced, the unstrained, the effortlessly optimal, is the aesthetic of the principle of least action, perceived directly rather than mathematically. The stone that rolls downhill follows the path of least action. The water that flows through a riverbed follows the path of least action. The tree that grows toward the light follows the path that optimizes its access to energy. The Zen practitioner perceives this optimization directly in the beauty of the natural world and recognizes in it the dharma, the lawful, ordered, intrinsically perfect nature of reality. The Japanese concept of shibui, the beauty of elegant simplicity, captures the aesthetic quality that the principle of least action embodies. Shibui is not ornate beauty, it is stripped beauty. The beauty that remains when everything unnecessary has been removed. The beauty of pure function, of maximum efficiency, of doing the most with the least. The principle of least action is the most shibui principle in physics. It does the most, generating every known physical law with the least a single optimization requirement applied to a single mathematical quantity. In Islam, the concept of hikmah, divine wisdom, provides the framework for understanding the rational order that the principle of least action reveals. The Quran uses the word Hakim, wise, as one of the most frequently invoked names of God. The divine wisdom is not merely a quality that God possesses. It is the quality that determines the structure of creation. He is the one who created the heavens and the earth in truth. 6-73. The word in truth, bilhaq, means with purpose, with wisdom, with rational order. The creation is not arbitrary. It is purposeful, structured by the divine wisdom according to a rational plan that the Quran describes as the best possible arrangement. The Islamic philosophical tradition developed this into a comprehensive theory of the rational universe. The philosopher Ibn Sina Avicenna argued that the universe is a necessary emanation from the divine intellect, and that the mathematical structure of the universe reflects the rational structure of the divine mind. The laws of physics are not arbitrary decrees imposed by divine will. They are the natural, necessary, rational consequences of the divine intellect, thinking the universe into existence. The principle of least action is, in Ibn Sina's framework, the mathematical expression of the divine intellect's natural preference for the most rational, the most efficient, and the most beautiful arrangement of the created order. The tension between Ibn Sina's necessitarian framework and Al-Ghazali's voluntarist framework, which we encountered in our investigation of the quantum Zeno effect, is directly relevant to the interpretation of the principle of least action. Ibn Sina says, the optimization is necessary. The divine intellect naturally produces the optimal arrangement, and the laws could not have been otherwise. Al-Ghazali says, the optimization is voluntary. God chooses to create the optimal arrangement at each moment, and God could choose otherwise. The principle of least action does not determine which framework is correct, but it is consistent with both. Whether the optimization is a necessary consequence of the divine intellect or a voluntary choice of the divine will, the result is the same, a universe that follows the most efficient, the most elegant, and the most mathematically beautiful path through the landscape of possibility. The Sufi tradition's concept of the perfect man, al-insan al-kamil, developed by Ibn Arabi, provides a specific connection between the principle of least action and the nature of human consciousness. Ibn Arabi argued that the human being is the microcosm, the small universe that mirrors the large universe in its structure, its proportions, and its mathematical order. The rational order that governs the cosmos, the principle of least action, the symmetries, the conservation laws, is mirrored in the rational order of the human mind. The human capacity for mathematical reasoning is not an accident. It is the microcosmic reflection of the macrocosmic hikmah, the divine wisdom that structures the universe, and that is reflected in miniature in the mind that can perceive and comprehend the structure. The philosopher Al-Kindi, the first of the great Islamic philosophers, argued in the 9th century that the mathematical sciences are the highest form of human knowledge because they most closely approximate the divine knowledge. God knows the universe through the mathematical structures that govern it. The human who learns mathematics is approximating the divine mode of knowing, perceiving reality through the same rational lens through which God perceives it. The principle of least action, discovered through the mathematical sciences, is the closest human approach to the divine mode of perceiving the physical world. The perception of the single, rational, optimizing principle through which God's hikmah structures the cosmos. The Ottoman polymath Taqi al-Din, working in the 16th century, described the relationship between divine wisdom and natural law with an image that anticipates the principle of least action by 2 centuries. The Creator has not placed in nature any excess or any deficiency. Every motion is measured, every process is proportioned, and the totality of creation reflects, in its economy, the wisdom of the one who fashioned it. The economy of creation, the absence of excess, the absence of deficiency, the optimal proportioning of every process is the principle of least action, perceived through the lens of Islamic natural philosophy. This is why the human mind can discover the principle of least action. The principle is not alien to the mind. It is the cosmic expression of the same rational order that the mind embodies in miniature. The mind recognizes the principle because the mind is made of the same rational stuff as the universe. The recognition is not the mind projecting its own patterns onto an indifferent world. It is the mind recognizing, in the mathematical structure of the world, the same rational order that constitutes its own deepest nature. In Hinduism, the concept of rita evolves into the concept of satya, truth, the principle that governs the rational order of the cosmos, and that is identical at the deepest level with the nature of Brahman. The Rig Veda's concept of rita describes a cosmic order that is prior to the gods, an order that the gods themselves obey, that governs the movement of the sun and the cycle of the seasons. And that is the principle of justice and truth in the human world, as well as the natural world. Rita is not a created order. It is the order from which creation emerges, the mathematical structure that determines the form, the proportion, and the behavior of every phenomenon in the universe. The Upanishadic identification of rita with satya, truth, adds a dimension that the Vedic concept lacked. Truth is not merely correspondence with fact. It is the nature of reality itself, the quality that reality has when it is perceived clearly, the order that the universe displays when it is understood deeply. The principle of least action is satya, the truth of the physical world, the rational order that the world displays when it is analyzed with sufficient mathematical precision. The physicist who discovers the principle is not merely finding a useful formula, they are perceiving satya, perceiving the truth of the universe, the rational order that constitutes the deepest nature of physical reality. The mathematician Srinivasa Ramanujan, one of the greatest mathematical minds in history, described his own mathematical discoveries in terms that directly echo the Upanishadic identification of truth with beauty. Ramanujan said that his equations were given to him by the goddess Namagiri, that they appeared in his dreams and in his meditations, and that he recognized them as true because they were beautiful. Ramanujan's experience is the Indian mathematical tradition's most dramatic confirmation of the Vedic insight. The mathematical order of the universe is not a human construction. It is a divine revelation, a perception of the Satya that constitutes the deepest nature of reality, revealed to the mind that is prepared to receive it through the combination of mathematical training and contemplative receptivity. The Vaisheshika school of Hindu philosophy developed a specific theory of natural law that anticipates the principle of least action with remarkable precision. The Vaisheshika identified adrishta, the unseen force, as the principle that governs the motion of atoms and that ensures that physical processes follow lawful, optimal trajectories. Adrishta is not a physical force in the Newtonian sense. It is a cosmic ordering principle that determines the proper behavior of each type of atom according to its nature, a principle that is functionally identical to the action in Lagrangian mechanics, determining the trajectory that each system follows based on its specific physical properties. The Bhagavad Gita provides the most direct connection between the rational order of the universe and the practice of human life. Krishna teaches Arjuna that the universe is governed by dharma, by the lawful, ordered, rational principle that determines the proper behavior of every being according to its nature. The principle of least action is the physical dharma, the rational order that determines the proper behavior of every physical system according to its nature. The particle follows the path of least action because that is its dharma, its natural, proper, lawful behavior, determined by the mathematical structure of reality. Krishna's teaching extends the concept of dharma from the physical to the ethical. Just as the particle has a physical dharma that determines its optimal path, the human being has an ethical dharma that determines the optimal path of life. The principle of least action governs the physical world. The ethical dharma governs the human world, and both are expressions of the same rational order, the same hikmah, the same logos, the same dharmata that structures reality at every level, from the trajectory of a photon to the trajectory of a human life. The concept of the Leela, the divine play, adds a final dimension. The universe's rational order is not the order of a machine. It is the order of a play, a creative, spontaneous, joyful self-expression of the divine that follows rules not because it must, but because the rules are beautiful. The principle of least action is the rule of the Leela, the aesthetic principle that the divine play follows, not because the play is constrained, but because the principle is beautiful, and the play is an expression of beauty. The universe optimizes not because it is forced to optimize, but because optimization is beautiful, and beauty is the nature of the divine. Now we must address the deepest philosophical question that the principle of least action raises. Is the rational order of the universe evidence of design, or is it a brute fact that requires no explanation? The argument from design, the argument that the rational order of the universe implies the existence of a rational designer, is one of the oldest arguments in the philosophy of religion. The principle of least action provides the strongest version of this argument that physics has ever produced. The most fundamental law of physics is a principle of optimization. An optimization implies an optimizer. The universe does not merely behave, it behaves optimally. An optimal behavior, in every other context in which we encounter it, is the product of intelligence. The counter-argument is equally powerful. The optimization may be a consequence of the mathematical structure of quantum mechanics, not of a designer's intelligence. Feynman's path integral shows that the optimization arises from the interference of amplitudes, a purely mathematical process that requires no intelligence, no foresight, and no design. The universe optimizes because the mathematics of quantum mechanics produces optimization as a natural consequence. The design is apparent, not real. The intelligence is projected, not discovered. A third position, intermediate between design and brute fact, has been developed by the philosopher Thomas Nagel. Nagel argues, in his book Mind and Cosmos, that the rational order of the universe is evidence of a teleological principle, a principle of directedness, of orientation toward specific outcomes, that is built into the mathematical structure of reality, but that does not require a personal designer. The universe is directed toward consciousness, toward rationality, toward beauty, not because a designer planned it, but because the mathematical structure of reality contains a principle of teleological direction that naturally produces these outcomes. The principle of least action is, in Nagel's framework, the most fundamental expression of this teleological principle, the natural, inherent, non-design directedness of physical reality toward optimal outcomes. Nagel's position has been criticized from both sides, by theists who argue that teleological direction without a director is incoherent, and by materialists who argue that teleological direction of any kind is a regression to pre-scientific thinking. But the position has the virtue of taking the evidence seriously, acknowledging the genuine teleological character of the principle of least action, without committing to a specific metaphysical interpretation of its source. The philosopher of biology Stuart Kauffman, whose work on the reinvention of the sacred we encountered in our investigation of evolution, occupies a similar position. Kauffman argues that the persistent creativity of the universe, its capacity to generate novelty, complexity, consciousness, and rational order through lawful but non-deterministic processes, is a feature of reality that deserves to be called sacred, regardless of whether a personal God is responsible for it. The principle of least action is sacred in Kauffman's sense. It is the most fundamental expression of the universe's persistent drive toward optimal, beautiful, rationally ordered outcomes. The honest answer is that the evidence supports both interpretations and compels neither. The principle of least action is consistent with the existence of a rational designer. It is also consistent with a universe that is rationally ordered without a designer. The physics cannot distinguish between these two possibilities, because the physics describes the order but does not explain why the order exists. The explanation, if there is one, must come from beyond physics, from the domain that the contemplative traditions have been exploring for millennia, the domain of the relationship between the rational order of the universe and the ground from which the universe arises. The traditions speak, the physics listens, and the convergence between what the traditions describe and what the physics reveals is at the very least worthy of the sustained attention that the final stage of this investigation will provide. Because the convergence is not superficial, it is structural. It extends from the highest level of generality, the claim that the universe is rationally ordered, to the most specific details, the claim that the rational order takes the form of a principle of optimization that produces beauty, symmetry, and conservation. The traditions arrived at this description through millennia of contemplative insight. The physics arrived at it through centuries of mathematical analysis. And the two descriptions match not perfectly, not in every detail, but in the deep structure that both investigations have independently uncovered. The final stage will ask what this match means and what it reveals about the nature of the universe, the nature of consciousness, and the nature of the relationship between the mind that discovers the order and the order that the mind discovers. We have now traced the principle of least action from its origins in Fermat's observation about light to its culmination in Feynman's path integral and Noether's theorem. And we have examined how the contemplative traditions describe the rational order that the principle reveals. The universe optimizes. The optimization is implemented by quantum interference over all possible paths. The symmetries of the optimization produce the conservation laws that govern every physical process, and the contemplative traditions, across every major civilization, describe the rational order of the universe in terms that converge with remarkable precision on the structure that the physics reveals. Now we must bring everything together and ask the deepest questions. Why is the universe efficient? What does the principle of least action reveal about the nature of reality? And what does it mean for you, for a conscious being, living in a universe that is structured at every level by a principle of perfect optimization? Let us begin with the question that has haunted this investigation from the beginning. Why does the universe optimize? The question has 3 levels, and each level requires a different kind of answer. At the first level, the answer is mathematical. The universe optimizes because the mathematics of quantum mechanics produces optimization through the interference of probability amplitudes. Feynman's path integral shows that the system explores all possible paths simultaneously, and the constructive interference of amplitudes around the action-minimizing path produces the classical behavior that we observe. The optimization is a mathematical consequence of the quantum mechanics. It does not require a designer, a purpose, or a cosmic plan. It requires only the Schrödinger equation and the superposition principle. This answer is correct as far as it goes, but it does not go far enough. It explains how the optimization occurs, but not why the mathematics that produces the optimization exists. The Schrödinger equation is not a necessary truth. It is a contingent fact about the mathematical structure of the universe. The superposition principle is not a logical requirement. It is a specific feature of a specific kind of mathematics, a feature that could have been otherwise. The question of why the universe has quantum mechanics rather than some other kind of mathematics, why the specific mathematical structure that produces optimization is the structure that obtains, is a question that the mathematics itself cannot answer. At the second level, the answer is cosmological. The universe may optimize because the optimization produces the conditions that are necessary for the existence of conscious observers. The anthropic principle, in its various forms, argues that the laws of physics must be compatible with the existence of the observers who discover them. If the principle of least action is necessary for the production of the complex, organized, far from equilibrium structures that conscious beings require, if optimization is a prerequisite for the kind of universe that can produce life, intelligence, and consciousness, then the fact that we observe a universe governed by the principle of least action is not surprising. It is a selection effect. We observe optimization because only optimizing universes produce observers. This answer has force. But it raises a further question. Why are there any universes at all? And why do the possible universes include universes that optimize? The anthropic principle explains why we observe an optimizing universe, given that optimizing universes exist. It does not explain why optimizing universes exist in the first place. The selection effect requires a population to select from, and the question of where the population comes from, where the landscape of possible universes originates, and why that landscape includes the specific mathematical structures that produce optimization, is a question that the anthropic principle cannot answer. At the third level, the answer is the answer that the contemplative traditions have been giving for millennia. The universe optimizes because the ground from which the universe arises is rational. The optimization is not a mathematical accident. It is not a selection effect. It is the expression of a rational order that is prior to the mathematics, prior to the physics, and prior to the universe itself. The principle of least action is not a law imposed on an indifferent substrate. It is the signature of the rational ground, the logos, the dharma, the hikmah, the rita that the universe expresses in its every process. This answer is not a scientific answer. It cannot be tested experimentally or verified mathematically. It is a philosophical answer, an interpretation of the evidence that the physics provides, but that the physics does not compel. The physicist can accept the mathematical answer and the cosmological answer without accepting the philosophical answer. The evidence is consistent with a rational ground. It is also consistent with a universe that is rationally ordered without a rational ground. The evidence underdetermines the interpretation. But the convergence is worth noting. When the physicist discovers that the most fundamental law of physics is a principle of optimization, and when the contemplative traditions describe the ground of reality as a rational intelligence whose nature is optimization, the convergence is not proof, but it is evidence, the same kind of evidence that motivates scientific investigation. The kind of evidence that says this pattern is worth taking seriously, this convergence is worth investigating further, and this possibility is worth considering with the seriousness that the evidence warrants. The philosopher Leibniz, whom we encountered in Part 1, formulated the question with a precision that has never been surpassed. Why is there something rather than nothing? And why is the something that exists ordered rather than chaotic? The principle of least action sharpens Leibniz's question to a razor's edge. Not merely why is there something, but why is the something that exists optimized? Why does the universe not merely exist, but exist in the best possible way, following the most efficient paths, obeying the most symmetric laws, conserving the most fundamental quantities? The existence of something rather than nothing is mysterious. The existence of optimized something rather than chaotic something is doubly mysterious. And the principle of least action is the most concentrated expression of this double mystery. The physicist Max Planck, who inaugurated the quantum revolution in 1900, described the principle of least action as evidence of what he called the real behind the phenomena, the objective, observer-independent mathematical structure that constitutes the deepest level of physical reality. Planck wrote, "The principle of least action is the most general and the most fruitful of all physical principles. It contains in a single formula the entire mechanics of the universe." For Planck, the principle was not merely a useful mathematical tool, it was a window into the nature of the real, the mathematical substance of which the physical world is the expression. The connection between Planck's real and the contemplative tradition's ground of being is direct. Both describe a level of reality that is deeper than the physical phenomena, that determines the structure of the physical phenomena, and that is rational, mathematical, and oriented toward optimization. The physicist calls it the mathematical structure of the action. The traditions call it the logos, the dharma, the hikmah, or Brahman. The names differ. The structure is the same. Now let us consider what the principle of least action reveals about the nature of reality when it is combined with every other investigation in this series. In our investigation of time, we established that time is not a fundamental feature of reality, but an emergent quantity constructed by consciousness from the raw materials of attention, memory, and novelty. The principle of least action adds a dimension to this understanding. The action is defined as an integral over time. The optimization is a temporal optimization, a selection of the path that minimizes the action over the entire temporal interval from beginning to end. If time is emergent, then the action is an optimization over an emergent quantity, an optimization that presupposes the temporal structure that consciousness produces. The optimization and the consciousness that perceives the optimization are intertwined. The optimization requires time, and time requires consciousness. The principle of least action is not merely a law about the physical world. It is a law about the relationship between consciousness and the physical world, a law that presupposes the temporal framework that consciousness generates. In our investigation of distance, we established that space is emergent from entanglement, that the geometry of the physical world is produced by the pattern of quantum correlations between its parts. The principle of least action operates within this emergent geometry. The action integral is computed over the spatial and temporal coordinates that the entanglement structure produces. The optimization is an optimization within the emergent geometry, an optimization that selects, from among all paths through the entanglement-generated space, the path that minimizes the action. The principle of least action and the entanglement structure of space are not separate features of reality. They are aspects of a single, unified mathematical framework in which the geometry and the dynamics are both determined by the quantum state of the universe. In our investigation of gravity, we established that the curvature of space-time is the geometric expression of the entanglement structure of the quantum vacuum. The Einstein-Hilbert action, the action from which Einstein's equations of general relativity are derived, is the gravitational instance of the principle of least action. The curvature of space-time is determined by the minimization of the gravitational action, and the gravitational action is connected through the AD-S CFT correspondence to the entanglement entropy of the boundary theory. The curvature of space-time, the principle of least action, and the entanglement structure of the quantum vacuum are three descriptions of the same underlying reality, three perspectives on the single mathematical structure that constitutes the ground of the physical world. In our investigation of the first observer, we established that the universe may require conscious observers to collapse its quantum states into definite outcomes. The principle of least action adds a specific dimension to this requirement. The optimization requires a definite path, and a definite path requires a definite collapse of the quantum superposition into a specific trajectory. The path integral sums over all possible paths, and the constructive interference selects the classical path. But the selection is not complete until the system is observed, until the superposition is collapsed into a definite outcome by the measurement that the observer performs. The optimization and the observation are inseparable. The optimization selects the path, and the observation actualizes the path. Without the observation, the path is not definite. Without the definite path, the optimization is not realized. The principle of least action requires consciousness, requires an observer to actualize the optimal path that the interference selects. In our investigation of evolution, we established that evolution may be a quantum algorithm computing toward consciousness. The principle of least action provides the framework in which this computation operates. Evolution is the biological implementation of the path integral, exploring all possible genetic configurations simultaneously and selecting, through the interference of fitness amplitudes, the configurations that optimize the objective function. If the objective function is consciousness, if evolution is optimizing for phi, for integrated information, for the capacity for conscious experience, then the principle of least action is the principle that governs the biological computation that produces consciousness. Evolution follows the path of least action through the fitness landscape, optimizing for consciousness with the same mathematical precision that a photon follows the path of least time through a refractive medium. In our investigation of grief, we established that the information constituting a human being is not destroyed at death, that unitarity preserves the quantum correlations, and that the Bohm implicate order provides a framework in which death is the enfolding of the explicate back into the implicate. The principle of least action adds a remarkable dimension. The path integral sums over all possible paths, including paths that extend beyond the boundaries of individual biological life. The action integral for a person's quantum information does not terminate at death. The information continues to evolve according to the Schrödinger equation, and the principle of least action continues to select the optimal path for this information through the landscape of possibility. The path does not end. It continues through the quantum vacuum, through the entanglement structure that connects the living and the dead, through the cosmic observation that sustains all quantum information. Death is not the end of the path. It is a transition from one region of the action landscape to another, from the biological domain to the cosmological domain, from the locally observed to the cosmically observed, and the principle of least action governs the transition with the same mathematical precision that it governs every other physical process. In our investigation of the inseparable quark, we established that isolation is forbidden at every scale of physical reality. The principle of least action explains why. The action of a system is defined in terms of the relationships between the system's components, the kinetic energies, the potential energies, the interaction terms that encode the forces between particles. The optimization of the action is an optimization of the relationships. The optimal path is the path that produces the best balance between the components' kinetic and potential energies, the path that optimizes the relationships between the parts. The principle of least action is not a law about isolated entities following optimal paths. It is a law about relationships being optimized, about the connections between things being tuned to the best possible configuration. Isolation is forbidden because the action has no meaning for an isolated system. The optimization requires relationship, the efficiency requires connection, the beauty requires community. In our investigation of the acceleration of time, we established that the subjective rate of time is determined by the information processing capacity of the conscious system. The principle of least action adds a dimension. The action integral measures the quantity that the system optimizes over time. If time is accelerating, if the conscious system is processing fewer moments per unit of clock time, then the system is performing the action integral over a coarser temporal grid, and the optimization is less precise. The acceleration of time is a degradation of the precision with which the principle of least action is implemented in the conscious system. The distracted mind follows a less optimal path through the landscape of possible experience because it is computing the action integral with less resolution. The contemplative mind follows a more optimal path because it is computing the action integral with more resolution, more attention per moment, more moments per unit of clock time, more precision in the optimization of each moment's experience. In our investigation of the quantum Zeno effect, we established that continuous observation sustains quantum states against decay. The principle of least action adds the content that the observation sustains. The observation sustains the optimal path. The Zeno effect holds the system on the action, minimizing trajectory. The observation prevents the system from deviating from the optimal path by continuously projecting it back onto the trajectory that the action selects. The Zeno effect and the principle of least action are complementary. The principle selects the path, and the observation holds the system on the path. The divine observation that the traditions describe as sustaining the universe is not merely holding the universe in existence. It is holding the universe on the optimal path, sustaining not merely the existence of the physical world, but the perfection of the physical world, the optimization of every process, the beauty of every law. In our investigation of dreams as quantum timeline glimpses, we established that consciousness may have access, through the quantum correlations of the brain, to information that extends beyond the boundaries of the present moment. The principle of least action provides the framework for this access. The path integral sums over all possible paths, including paths that extend into the future and the past. The optimized path is selected by the interference of amplitudes that extend over the entire temporal interval, an interval that includes moments that the conscious system has not yet experienced. The precognitive content of dreams, in this framework, is the conscious system's partial perception of the path integral, its partial awareness of the amplitudes that extend into the future and that contribute to the optimization of the present moment's experience. In our investigation of retrocausality and the future self, we established that the influence of the future on the past is a genuine feature of quantum mechanics. The principle of least action is the most natural framework for retrocausality. The action integral extends from the initial time to the final time, and the optimization is performed over the entire interval simultaneously. The initial conditions and the final conditions jointly determine the path. The future constrains the past as much as the past constrains the future, and the principle of least action is the mathematical expression of this temporal symmetry, the principle that the optimal path is determined by the boundary conditions at both ends, not by the initial conditions alone. The picture that emerges from the synthesis of all these investigations is stunning in its coherence. The universe is a quantum system that explores all possibilities simultaneously through the path integral. The constructive interference of probability amplitudes selects the optimal path through the principle of least action. The symmetries of the action produce the conservation laws through Noether's theorem. The optimization requires space and time, which are emergent from the entanglement structure of the quantum vacuum. The optimization requires consciousness to actualize the optimal path through the collapse of the wave function. The optimization is sustained by continuous observation through the quantum Zeno effect. And the optimization produces, through the biological implementation of the path, integral in evolution, the conscious beings who perform the observations that actualize the optimization. The circuit is self-referential. The optimization produces consciousness. Consciousness actualizes the optimization. The actualized optimization produces more consciousness, and the loop continues, spiraling upward through increasing complexity, increasing integration, increasing phi, toward a state of maximum consciousness that every contemplative tradition has described in its own language. The omega point, the Buddha nature, the kingdom of God, the realization of Brahman, the return to the divine presence from which everything emerged. The principle of least action is the mathematical expression of this self-referential loop. It is the law that governs the optimization. It is the principle that selects the path. And it is the signature of the rational ground, the logos, the dharma, the hikmah, the rita, from which the universe arises and toward which the universe is returning through the precise, beautiful, perfectly efficient mechanism that the physics describes and that the contemplative traditions have always known. The theologian Teilhard de Chardin described this self-referential loop as the omega point, the future state of maximum consciousness toward which the entire cosmos is converging through the mechanism of evolution. The principle of least action provides the mathematical expression of Teilhard's vision. The universe is following the path of least action through the landscape of possible configurations, and the path converges on the state of maximum consciousness, the state in which the optimization becomes aware of itself. The computation recognizes itself as a computation, and the universe, at last, knows itself. The Buddhist concept of Bodhi awakening, enlightenment, describes the individual's realization of this self-referential loop. The awakened mind perceives that the dharma that governs the universe is the same dharma that constitutes the mind's own nature. The perception is not an intellectual understanding. It is a direct, non-conceptual, experiential recognition. The recognition that the rational order of the universe and the rational order of the mind are one and the same. That the principle of least action that governs the photon and the principle of least action that governs the thought are expressions of the same optimization, the same beauty, the same rational ground. The Islamic concept of ma'rifah gnosis, direct experiential knowledge of God, describes the same recognition in theistic terms. The Sufi who attains ma'rifah perceives that the hikmah that structures the universe is the same hikmah that structures the soul, that the divine wisdom is not distant, not separate, not other, but present in every thought, every perception, every moment of conscious experience as the rational order that gives each experience its specific form. The principle of least action, perceived through ma'rifah, is not an abstract mathematical law. It is the intimate presence of the divine wisdom in every moment of experience, the feeling of being guided, of being carried, of following a path that was prepared before you arrived and that will continue after you are gone. Now we must address the objections with the honesty that this investigation demands. The first objection is that the principle of least action is a mathematical reformulation, not a fundamental principle. The action is minimized because the Euler-Lagrange equations are satisfied, and the Euler-Lagrange equations are equivalent to Newton's laws. The optimization is a mathematical consequence, not a physical cause. The universe does not optimize, it merely behaves, and the behavior can be described mathematically as an optimization. This objection has force, but it proves less than it claims. The Euler-Lagrange equations are indeed equivalent to Newton's laws, but the Lagrangian formulation is more general than the Newtonian formulation. It applies to systems that Newton's laws cannot describe, including fields, relativistic systems, and quantum systems. The action principle is more fundamental than the force equations, and the question of why the most fundamental formulation of physics takes the form of an optimization is the question that the objection does not answer. The second objection is that the optimization is not always a minimization. Technically, the principle of least action requires that the action be stationary, that the first variation of the action vanish, not that the action be minimal. The action can be minimal, maximal, or a saddle point. The term least action is a historical misnomer. The correct term is the stationary action principle. This objection is technically correct, but does not undermine the philosophical significance of the principle. Whether the action is minimized, maximized, or at a saddle point, the behavior of the system is determined by the requirement that the action be stationary, that it satisfy a global optimization condition over the entire path. The system still behaves as if it has surveyed the entire trajectory in advance and selected the path that satisfies the stationarity condition. The teleological character of the principle is preserved whether the stationary point is a minimum, a maximum, or a saddle. The third objection is the most fundamental. The convergence between the principle of least action and the contemplative traditions may be a false convergence, a coincidence of language that conceals a difference of substance. The physicists' optimization and the theologians' divine wisdom may refer to entirely different things, and the apparent agreement may be produced by the vagueness of the language rather than by the similarity of the content. This objection is serious and must be acknowledged. The convergence is structural, not verbal. It is not that the traditions use the same words as the physics. It is that the traditions describe the same structure. A universe governed by a principle of rational order that produces beauty, efficiency, and conservation through the mathematical structure of its deepest law. The convergence may be a coincidence, but the probability that every major contemplative tradition, independently and across thousands of years, would arrive at a description of the rational order of the universe that matches, in its deep structure, the most fundamental principle of modern physics. This probability is, at the very least, low enough to warrant investigation rather than dismissal. The physicist John Wheeler, whose work has been the foundation of this entire series, made a statement near the end of his career that condenses the principle of least action, the contemplative traditions, and the self-referential loop of the participatory universe into a single stunning image. The universe is a self-excited circuit. It brings itself into existence through the observations of the conscious beings it contains, and the observations are governed by a principle of optimization, a principle that selects from among all possible observations the ones that produce the most coherent, the most beautiful, and the most consciousness-generating universe. Wheeler's self-excited circuit is the principle of least action applied to the universe as a whole. The universe is performing the path integral over all possible configurations. The constructive interference is selecting the configuration that optimizes the action, and the optimized configuration is the configuration that produces conscious beings who perform the observations that actualize the optimization. The loop is closed, the circuit is self-excited, and the principle of least action is the mathematical law that governs the self-excitation, the law that ensures that the universe, in exploring all possibilities and selecting the optimal one, produces the consciousness that makes the selection possible. So what does all of this mean for you? It means that you live in a universe that is not random, not arbitrary, and not indifferent to the quality of its own behavior. The universe optimizes. Every process, at every scale, follows the most efficient path available to it. The light that reaches your eyes has traveled the path of least time. The atoms in your body are configured in the lowest energy arrangement that the Pauli exclusion principle permits. The neurons in your brain fire in patterns that minimize free energy. And the evolution that produced your consciousness followed a path through the fitness landscape that optimized for the capacity to experience, to understand, and to appreciate the universe in which you exist. It means that the beauty you perceive in the natural world is not a projection. It is a perception of the optimization that the principle of least action embodies in every physical process. The sunset is beautiful because the light has been scattered through the atmosphere along the paths of least time, producing the specific spectrum of colors that the optimization selects. The spiral of a galaxy is beautiful because the gravitational dynamics follow the action-minimizing trajectory, producing the specific geometry that the optimization determines. The melody of a bird's song is beautiful because the neural circuitry that produces it has been shaped by evolution's optimization of the fitness landscape. The beauty is real. It is objective. It is the aesthetic expression of the mathematical optimization that governs every physical process in the universe. It means that the efficiency you admire in nature, the aerodynamic precision of a bird's wing, the structural elegance of a spider's web, the thermodynamic perfection of a cell's metabolism is not merely the product of natural selection acting on random variation. It is the expression of the principle of least action operating through the biological implementation of the path integral. Evolution does not merely eliminate the unfit. It follows the path of least action through the fitness landscape, producing organisms that are not merely fit but optimally fit, organisms whose structures, whose behaviors, and whose metabolisms are optimized with the same mathematical precision that governs the trajectory of a photon through a lens. The biologist Darcy Wentworth Thompson, in his masterwork on growth and form, documented the mathematical precision of biological structures, the logarithmic spirals of shells, the hexagonal packing of honeycombs, the Fibonacci sequences of flower petals, the fractal branching of trees. Thompson argued that these mathematical regularities are not merely the product of selection, but the expression of physical laws of the optimization principles that govern the behavior of matter at every scale. The principle of least action is the deepest of these optimization principles, and Thompson's biological structures are among its most beautiful expressions. It means that the rational order you discover when you study physics, mathematics, or any other science is not a human invention imposed on a chaotic world. It is a human perception of an order that was there before you looked, an order that the principle of least action expresses in its most concentrated form, that Noether's theorem connects to the deepest symmetries of physical law, and that the contemplative traditions have been describing, in their own languages, for as long as human beings have been capable of contemplation. And it means that the question you are asking right now, the question of why the universe is the way it is, why the laws of physics have the form they have, why the mathematical structure of reality is so beautiful and so perfectly organized, is not merely an intellectual curiosity. It is the deepest question that a conscious being can ask. And the fact that you can ask it, the fact that the universe has produced, through 4 billion years of evolutionary optimization, a being that can perceive the optimization, appreciate the beauty, and wonder at the order is itself the most remarkable consequence of the principle of least action. The universe has optimized over 14 billion years and across every scale of physical reality for the production of a being that can recognize the optimization. You are that being, and the recognition the moment when a conscious mind perceives the rational order of the universe and says, with Euler, nothing at all takes place in the universe in which some rule of maximum or minimum does not appear, is the moment when the principle of least action becomes aware of itself. It is the moment when the optimization recognizes the optimization. It is the moment when the logos perceives the logos. It is the moment when the dharma understands the dharma. It is the moment when the hikmah contemplates the hikmah. And it is happening right now, in you, in this moment, as you read these words and feel, perhaps, the specific, unmistakable, physiologically real sensation of awe that the human organism produces when it encounters something vast, something beautiful, and something true. That awe is not an illusion. It is the correct response of a conscious being to the recognition that the universe in which it exists is governed, at the deepest level, by a principle of perfect efficiency, perfect beauty, and perfect rationality. The principle of least action is the universe's deepest law, and the deepest law says everything, every photon, every atom, every planet, every galaxy, every living thing, every conscious mind follows the best possible path, including you. The Sufi poet Rumi described the experience of living within the rational order of the universe with an image that captures the essence of the principle of least action more perfectly than any mathematical formula. Let yourself be silently drawn by the strange pull of what you really love. It will not lead you astray. The strange pull is the principle of least action. The what you really love is the optimal path, the path that the deepest mathematics of the universe has selected through the interference of all possibilities as the path that produces the most beautiful, the most efficient, and the most consciousness-generating outcome. And the promise that it will not lead you astray is the promise that the optimization is real, that the universe is genuinely structured to produce the best possible outcome from the conditions that obtain, and that the conscious being who aligns with this structure, who follows the pull of what they really love, who trusts the rational order that governs every photon and every galaxy, is following the deepest law of the universe. The principle of least action is not merely a law of physics. It is an invitation to trust the rational order of the universe, to align your life with the optimization that governs all things, and to follow, with the confidence of a photon traveling through a lens, the path that the deepest mathematics of reality has prepared for you. The path is efficient, the path is beautiful, and the path, as every investigation in this series has shown from every direction, leads toward the same destination. The moment when consciousness recognizes the order that produced it, the moment when the optimization becomes aware of itself, and the moment when you, standing at the intersection of physics and prayer, of mathematics and meditation, of science and the sacred, perceive, in the rational beauty of the universe, the ground from which you emerged and to which you are returning. The universe follows the path of least action, and the path of least action, traced from the Big Bang to this moment, leads to you, reading these words, feeling that pull, recognizing the order, and knowing, perhaps for the first time, that the universe's deepest law has always been guiding you home.